Monarchs of Memory, it's Prof. Gene. In this lesson, we're going to learn how to expand your Pico board's memory capacity by adding an SD card. After adding CircuitPython libraries to a Pico, your free memory often can be measured in kilobytes, but after installing a less than $4 microSD memory card reader, you'll have the potential to expand your Pico storage by gigabytes. The hardest part of this is the wiring, which requires 6 wires in total, but the code is super easy. I'll show you how to get this working, and we'll use that extra storage to play a bunch of audio files. We'll learn a bunch of additional things along the way, including about the SPI protocol and how it compares with I2C. We'll write our first reusable module, and we'll learn to stop playing of audio files at any time. Let's convert that big learning into big storage. So, legendary students, in this lesson we're going to be using the Adafruit microSD SPI or SDIO card breakout board. And at the time I'm recording this lesson, this diminutive brain expander is only $3.50 US. What a bargain! There's a good chance you spent more than that on your last latte. Yet this bad boy will last much longer. And if you've got an SD card, 32 gig or smaller is recommended, then you can blast your storage capability so that you'll be able to load all sorts of sounds, images, or anything else you'd like on your Pico. Now this breakout comes with unsoldered headers, so to work with this on a breadboard like I'll demonstrate, you'll need to solder those on, and you'll also want a breadboard and at least 6 pin jumper wires. Pro tip, if you're going to be doing a lot of breadboard work on the Pico, this one here has labels for the Pico's pin names, which is super useful since the Pico does not have pin names on top of the breadboard itself. If you've been following CircuitPython school, we'd mentioned the big 3 communication protocols. So we've seen 2 of these already. We saw UART briefly mentioned when we were dealing with Bluetooth coding on the Circuit Playground Bluefruit. Now we haven't had to wire anything up for UART, but some devices will use UART wiring. Now we've also seen I2C, which is pronounced I2C. This is what StemmaQT uses. And now we're going to see SPI or SPI, which is used for our SD card reader. Now quick recap, I2C stands for Inter-Integrated Circuit Protocol. So I2C on the Pico was pretty straightforward. We used a StemmaQT connector, power always went to 3.3 volts, there are 2 extra wires, and for standard StemmaQT wiring, we had 2 standard colors, blue for data, yellow for clock for signal timing, and those go to pin GP4 and GP5 if you want to use this standard CircuitPython command. Now while you can change things up from this, it is nice to have standard pins, colors, and a statement. Also remember I2C implemented over StemmaQT allows you to daisy chain devices over a single 4-wire cable. Really easy to use. Now the main drawback of I2C is it's not very fast, and if you want to send lots of data like we want to do with an SD card full of audio files, then SPI becomes a better choice. SPI or SPI stands for Serial Peripheral Interface. Now SPI is less standard than I2C over StemmaQT. The wiring is more complex. There are 6 wires instead of 4. Those wires also don't have standard colors, and because pins aren't standard either, there's not a one-line implementation like we can get with StemmaQT on the Pico or on any board with a StemmaQT port. So for wiring, power should always be 3.3 volts, and this is really important for a micro SD card. If you accidentally use a higher power pin like VBus, you could damage your SD card, so always be sure to use 3.3 volt out for power. Now any ground is fine for ground, but the 4 other wires are clock for signal timing, and there are 2 data wires in SPI, not 1 like in I2C. There's SI or MOSI, which stands for main out or microcontroller out, secondary in, so this goes from the microcontroller in our case, the main, to the secondary device, that's the SD card reader in our case. And there's an SO or MISO, which goes in the opposite direction, the main or microcontroller in, so in our case that's data coming from the SD card reader. And each device also needs a dedicated CS pin, which tells the main device or microcontroller that it needs to listen to and respond to requests from the connected device. Now since every connected device needs a CS wire, that also means that you can't daisy chain devices on a single cable like you can with StemmaQT. Now even though there's no recommended wire color or pin use, for this build I've used yellow for my clock going into GP10. I've used the same color as the clock wire for StemmaQT. And even though I've used GP10, if you look at a Pico pin diagram, you can use any of these SPI pins that are labeled SCK. That stands for clock, serial clock. Now I've also used blue for the data for SI or MOSI, and I'm wiring that to SP11. On the Pico you can choose any of the pins that are labeled TX. TX stands for transmission, meaning you're transmitting from the microcontroller. And I've used green for SO or MISO, which I've wired to GP12. You can use any of the RX pins for SO or MISO. RX stands for receive, meaning the microcontroller is receiving from the secondary device. Now I've also used white for my CS wire, and this is going to GP13, but again you can choose any of the pins that are labeled CS. And of course, wires are wires. The color doesn't matter at all. So if you don't have these colors, use what you've got. But hopefully if I standardize on these colors, it'll make the wiring diagram that you're looking at easier to read, understand, and remember. So final overview, I2C is used in STEMIQT or QUIC, which is what SparkFun calls these devices. They actually came up with a standard. Adafruit extended it so it could be used with certain 5-volt devices. It's a slower scheme, so you'll see it used for low data devices like sensors, simple input devices like buttons or this rotary encoder, or even small tech-centric displays. Now, I2C over STEMIQT gives you a nice single cable hookup, and many devices have STEMIQT ports built in, and there's a single line of CircuitPython code that you can use to set up I2C on a Pico or any device with a STEMIQT port. Now, SPI is faster, so you see this used to implement devices that need to transfer lots of data quickly, like SD card readers or larger, more colorful displays. There are more wires, so wiring is more complex. Each device also needs its own CS wire, so there's no single cable daisy chaining like there is with STEMIQT devices. And since there are no standard pins, when you write code, you've got to label each pin in your code when you're setting things up. Now, do be aware that Adafruit has created an open standard called iSPI, EYESPI. You see their little logo right here, and this uses a special ribbon connection that lets you simplify wiring from port to device. You're starting to see this show up on more devices, which is really nice because it cuts down on the crazy wiring, soldering for permanent connections. It's nice and thin, and it's pretty secure. Unfortunately, the Pico and the SD card reader don't have iSPI ports, so we're going to wire everything. So here's my SD card breadboard wired up to my Pico. I use smaller 3-inch pin jumper wires here so that the wires are more contained. And remember, if you were doing a permanent build, you could of course solder things up. Now power goes to 3.3 volt out, ground to any ground. And then if you go left to right in this orientation, looking first at the SD card reader, I've got clock yellow, SO MISO RX, which is green, SI Mossy TX for blue, and CS white. And then I'm using this block of 4 pins on the Pico, GP10 through GP13. The blue and green are flipped directions going here though. So clock yellow goes to GP10, SI MISO TX is my blue wire going to GP11, SO MISO RX is green going to GP12, and CS white goes to GP13. Now before we code, we need to prep a microSD card with some files that we can use. So I'm going to format my SD card first. That's always a good idea when working with a new SD card, and it's an especially good idea for my students because they probably have SD cards that were used during the previous semester, and they've got a bunch of old files on them. Now you can get the free official SD card formatting program by searching online for SD card formatter. This should take you to the page for the SD Card Association. They provide formatting software for free. You might have to accept the terms of service first. Then open the file you just downloaded and open the installation program and follow any steps you're asked to install the software. When the install is done, you can throw away the folder you just downloaded, then open the SD formatting program that you just installed. I've got the Mac version here, and if you have an SD card reader, plug that into your computer and pop your SD card in. If your computer has a built-in port for an SD card, you can put your SD card into that. If your slot is longer, you might have to use an SD card adapter so that your microSD card can fit in the larger old-school SD card port. Most microSD cards were sold with these adapters, and you should see your card mounted on your computer. Now in the SD card formatting software, make sure that you're selecting your SD card using the Select Card menu. Make sure that you're not selecting your CircuitPython volume or any other external hard drive that's attached to your computer. You don't want to accidentally format something that's really important. Now my SD card happens to be named boot. Yours might have a different name or might be labeled untitled. My card's also a 32 gigabyte card, so I see that under capacity. Don't use any cards larger than 32 gigabytes. Currently, the card reader in CircuitPython can't handle anything larger than 32 gigabytes. Now, the quick format option should work fine, so select this, then click the format button. You might be asked for your computer's password to approve formatting, and this should be done very quickly. If you have a problem with your card, you can select the overwrite format, but that'll take several minutes to set up. It's a much longer format. Once your card is formatted, you can quit the SD card formatter software. Now, before we can continue, we've got to put some files on the card, and why don't you open a browser and head to bit.ly/circuitpython-school-files, all lowercase. That takes you to an open Google Drive. That's the drive with sample files that we use in our course. Then why don't you right-click and download the folder Robot Sounds, and while you're here, why don't you also right-click and download on the folder called Beats_22K. That's the folder we'll use in our challenge. We'll put them both on the SD card because we've got lots of room. Then you can close your browser, find both of those folders you've just downloaded, and I'm going to drag them both into my SD card that I just set up. Now, if you take a look at these folders, you'll see Robot Sounds sounds has files named 0.mp3 through 12.mp3 and a couple of startup files. And the folder beats_22k doesn't have mp3 files. It's got a bunch of WAV files. And I've saved these at the 22,000 Hertz format, which means that these files are larger and higher quality than the ones we used in our DJ board lesson. Hopefully you'll hear an improvement when using these files. For now, we'll play the sounds in robot_sounds, and then in the challenge, we'll use the other files. Then I can eject my SD card, take it out of the card reader, and plug it into the breakout board that's attached to the Pico. I'll hear a little snap when I push it in and it's connected. To take it out, you give it another little push and you'll hear another snap and the card will pop out a bit, but let's leave it pushed in. Then I'll plug my Pico into my computer's USB, I'll open Moo, and we're ready to code. Oops, and I almost forgot, since we're going to be playing audio on the Pico, I just wired up a speaker, tip is clipped to audio in, sleeve is to ground, just like in our prior lessons, and here the audio in from the tip is headed to GP15. Now back to Moo. So I'll start with a comment playing audio from an SD card, and I'm going to import board, time, bus IO, SD card IO, storage. Then we need to set up the 4 pins for SPI. There are 6 pins, but one's power and one's ground, and those aren't in our code. So we need a clock pin. I'm going to name that SCK, lowercase, setting that equal to board.gp10. That's going to be my yellow wire, but your wire color might be different. SI equals board.gp11. My wire's blue. SO, and that's the letter O, not 0, I've already made that mistake twice, equals board.gp12, that's green, and CS equals board.gp13, that's white. And I wrote the comment yellow in here. I should have wrote the comment white. Sorry about that. Then we'll create our SPI object. I'm going to call that lowercase SPI, and I'll set that equal to busio.S, P, I, and in parentheses, I'll pass in my SCK, SI, SO. So those are my clock, my input, my output pins. Then I create my SD card object. I'm going to call that SD card, all lowercase, setting it equal to SD card IO dot S, D, C card. And then in parentheses, I pass in my SPI object, and CS, which is my control pin. Then I need to create an object of class type VFS FAT. That's not body shaming. VFS is virtual file system and FAT is file allocation table. It's a common method for organizing files. And when we create an object of this class, we're going to have all the logic CircuitPython needs in order to be able to translate its calls into what it needs to access the microSD card. So I'm going to call my VFS object VFS in lowercase, set that equal to storage.V, lowercase fs, capital F, lowercase at, and I just need to pass in my SD card object that I created in the line above. Then I say storage.mount, and in parentheses, VFS, and then in between double quotes, the string /SD. That just mounts the SD card, and I can refer to anything on the SD card from the root directory /SD, and you'll see this below. Now, before we get there, first let's set up audio. So from audio MP3, we're going to import capital MP3, capital D coder. From audio PWMIO, we import capital P, capital W, capital M, capital A, audio capital O out, as capital A, audio capital O out. These are all things we learned about in an earlier lesson. I'm going to create an audio object, all lowercase, and set that equal to capital A, audio, capital O out, and we pass in the pin that we clipped to the tip of our speaker, which is board.gp15. Then we're going to set our path equal to the string /SD, which gets us to the SD card, /robot_sounds/. So robot sounds is the folder that we want inside. All of these are lowercase. Note the SD to access the SD card volume. You'll always need that whenever working off of the SD card. And then in the next 3 lines, we perform all the steps we need to create an MP3 decoder, which is an object that's going to be able to play the MP3 files. So first we'll create a file name variable, and we'll set that equal to the number 0.mp3 in quotes. Then we'll load that file into a variable called mp3_files, setting that equal to open, and in parentheses path plus file name, and in quotes RB in lowercase, so that reads in the binary values of the file 0.mp3. And the reason we needed to get this mp3 file is that's needed in order to create a decoder. Even though we're not playing it now, we need to pass in an mp3 file when we set up the decoder. So we're going to call this by the variable name decoder, set it equal to mp3 decoder with the mp and the d all capitalized, and we're going to pass in mp3_file. Then we'll write the function to play MP3 files, and you've seen this in our prior lesson. So we'll define this with def space play underscore MP3, and we're going to pass in between parens file name. Make sure there's a colon at the end of this line. And then inside the function, the first line is going to be decoder.file equals, and we're going to open the file name here as well. So I'm just going to highlight the open statement that I have up here to the right of this equal sign, copy it, and paste it down below to the right of this equal sign. Then with MP3 files, we don't play the file, we do an audio.play passing in decoder. Then on the next line, we'll say while audio.playing colon, and underneath that pass. But we could replace pass with anything that we would want to run while the sound is playing. Then down below what we'll do is we'll just play 13 files that are in our robot sounds folder, and those sounds are named 0.mp3 through 12.mp3, so I'll just say for I in range 13 colon, so there are sounds 0.mp3 through 12.mp3, and then I'll set up my file name just below this, indented, file name equals, and I'll use an F string to create this, so I'll say lowercase f, and in between double quotes, curly braces I.mp3. Below this I'll print out the file name, so I'll say print, and in between parentheses, F, double quote, playing colon, curly braces file name. Make sure you have the closing double quote and the closing paren. Then I'll say play underscore MP3, passing in file name in between parens. We'll open the serial console. Make sure that you've got your speaker turned on. Sometimes I wonder why my code isn't working and my speaker isn't on, so I won't hear anything. And then let's click on save and listen to our sounds.
Bro, that's totally cool. Go set the world aflame. Keep at it, Eagle. Look at you making things. Nice job, maker. Nice work. Study hard. You've got this. Make something awesome. Hey there, want some candy? Reach in and grab a snack. Watch out, I'm on a roll. You go, girl. Hey there, you look smarter than ever today.
So these are sounds I have my robot play. We'll use them again in a later lesson when we build a remote-controlled robot, but they sound great. Now there's always a bit of a pop before playing a sound. In future lessons we'll discuss how you might get rid of that, but for now, mission accomplished. We have an SD card working on our Pico, and our Pico's memory is now 32 gigabytes large. Nice work! So I'm going to save this to my CircuitPython school folder as SD card with Pico, then close this and reopen code.py on my CircuitPy volume on my board, and now it's time for a challenge. So we just played a folder full of MP3 files that was called Robot Sounds, but earlier in this lesson you also downloaded a file full of WAV files that was called beats_22k. Now to make things easier for you, I've created a Google Doc at this URL, bit.ly/dj-board-names, and that contains the names of all of the files in the beats22 folder in strings, so you can just copy and paste them into your code so that you don't have to retype all those names yourself. In this challenge, you should add the NPR 12112 pad touch sensor that we used in an earlier lesson, then add the code to respond to each touch, and play a different wave file when a tone is touched. Remember, we just played MP3, so you want to switch to waves. Now, unfortunately, at this stage, we can't replicate the DJ board. There's a glitch when using Audio Mixer that won't let us read in and simultaneously play all of those multiple voices from the SD card. If there's a change in this, I'll be sure to add a new lesson. But we can still use the basic wave file playing code to play individual wave sounds from the SD card when a pad is touched. Now, even if you get this, stick around to watch the solution because I'm going to demonstrate a couple of things. One is we'll create a module, a file that we can add to our lib folder. And if we import that module, it'll automatically run all of the code we need to set up an SD card reader and mount the card so that we can use it in the Pico. This is a great thing to do to make your code more reusable. Then I'll also demonstrate how we can look up additional commands that are available for the audio out class, and we'll see that we can use a stop method on audio out objects that will stop a sound when playing when a finger is taken off the pad. So lots of learning to come, but try that basic solution on your own first. Pause. Give this a shot. You definitely have the skills to solve this challenge. And resume, and let's compare answers. So all the code we'll write in this first part is code that we've written before. First, since I'm not going to be working with MP3 files, I can delete this line here. Audio MP3 is not needed, but I do need to import the WAV file class, so I'll say from audio core import WAV file. That's with capital W, capital F. I also need to change the path, so I'm still in the SD card, but it's not going to be robot_sounds that I'm accessing. It's now beats_22k. Then all of the code below this line is related to playing MP3 files. I'm not going to do that, so I'm going to highlight all this code and delete it. Then I'm going to set up a list to hold strings that are the names of each of the files that I want to play. I'm going to call this beats. I'm going to set it equal to square brackets, but then I can head over to the web. I've already got this page open that you can find at bit.ly/dj-board-names, all lowercase, and I'm going to highlight all of these strings, copy it, Then head back to Moo and paste it between the square brackets, and I'll just adjust the indentation here so it looks nicer. Then I'll write my standard play sound function. You might have copied this from earlier code, which is fine, but I'll define the function with def space play underscore sound. I'm going to pass between parens file name, make sure there's a colon at the end. Then indented below this, I'm going to say with open and between parens path plus file name, comma, and then the string RB. And I'm going to save the data that I get this as wave underscore file colon. Indented below this, I'm going to create a variable called wave, and I'm going to set that equal to wave file, capital W, capital F. And I'm going to create a wave file object by passing in wave underscore file. That's the variable I created above. And now I've got a playable wave file, so I just say audio.play, passing in wave. Then underneath this, I'll say while audio.playing colon, and below this, pass. And remember, you can replace the pass with any code that should execute while playing, and we'll do that in our next example. So now that our wave files are all set up, let's head to the top of our code and we'll set up our MPR 121 sensor. We could have done this down below, but I think it's better to do it up top. That'll let us keep our audio stuff all nice and grouped. And first, I'll add as a separate import line, although I could have added it above as well, import Adafruit underscore MPR 121. Then we create an I2C object named I2C, setting that equal to board dot, and in all caps, stemma underscore I2C, open and close parens. Then we use that to create an MPR 121 object that I'll call touch underscore pad, setting that equal to Adafruit underscore MPR 121, the library we just imported, dot, and in all caps, MPR 121, passing in between parens I2C, the I2C object we created in the line above. Now that we've got this, we're ready for our while true loop with while true, capital T, colon, and below this we want to check out all of our pads. Now unfortunately we can't get a length of touch underscore pad, but we can get a length of beats, and we know we've got the same number of beats as pads, so I'll say for I in range, in parentheses, len, in parentheses, beats. Make sure you got a colon at the end. Then we'll check to see if any of the individual touch pads has been touched with if touch underscore pad in between square brackets I dot value colon. And if that pad is being touched, on the line below this, the last line in our code, play underscore sound in parentheses beats in between square brackets I. That plays the sound for that pad. Now let's open our serial console. We'll click save, no errors, and let's commence rocking. I'll make sure I've got my speaker turned on. You can see I've got my MPR 121 plugged in, and I'm using the same DJ board that I created in the previous lecture. So you can see the sound continues to play until it's done. That's because we've got a pass statement under while audio.playing.
Watch this.
So challenge complete, but why don't we make changes so that we can stop play when we take our finger off the pad, and I'll show you how we can take some of the code in this file and move it to a separate file for easy reuse. So I'll close the serial console and let's head to the top of our code to create our module file containing all of the code to set up our SD card. And you know what? Just so that we can see our code better, I'm going to highlight, cut out, and move the MPR 121 setup code so that it's below the SD card setup. Now all the SD card code is this code here that I've highlighted, from importing bus IO through the storage.mount statement. So I'm going to cut this out, and then I'm going to click on new to create a new file. And in this tab, I'll paste in the code that I just cut, and I'll add import in front of this first line. So these are all the libraries that I need to import. If I highlight bus IO in the import line, we can see all the other places in the code where bus IO is mentioned, and I can do the same for SD card IO and storage. Now I also see board in here, and I haven't imported board in this file. And as long as I import board in my main code, then that import will apply to this module as well. But if you want to be safe, you can also put board in the import statement here. Off the top of my head, I can't imagine a situation where you wouldn't have imported board in your main program, but there's no harm in leaving board in here just to be safe. And I'll add a comment at the top that says mount underscore SD will mount an SD card volume. And I'll double click the tab for this file, and I'm going to save it inside my CircuitPy volumes lib folder as mount underscore sd.py. So this will let me import it along with all of my other libraries, but I'll also double click on the tab again to save mount underscore sd to my CircuitPython school folder, so I've got a backup of this. You might also want to save it to your lib folder backup so that you can easily copy this over to your board when you need to do a lib folder reinstall. But now I can close this tab, I don't even need it up, and watch how I access it. So in my import line, I'll just add comma followed by mount underscore SD, and that's going to bring in all of the lines in that separate file. I don't need to retype them. Cool, huh? So this is a nice reusable module, and you can do this with any code you'd want to use, say setting up colors or things like that. Now let's explore how you'd stop a file from playing. So our command to play a file in our code is just audio.play. Now audio is an object we created that's from the class audioOut. So I'm going to search online for the documentation for audioOut to see if audioOut has any statement that I can use to stop playing audio. So in my browser, I'm going to search for read the docs, one word, Adafruit, CircuitPython, audioOut. Read the docs is the name of the website that hosts most of the CircuitPython documentation. I'm not sure what this first URL is. It says CircuitPython-Jake at read the docs. Maybe it's legit, but I'm going to go to this one down here. And it's interesting. It looks like this one is hosted at circuitpython.org, not read the docs. So I don't know if the docs are split or if they're in transition, but if we click on this doc, we see it brings us to the documentation for the Audio I/O library, and down below we can see audioOut is mentioned. And if we scroll below this, we can see that there are a bunch of methods for audioOut, including playing, paused, play, and look at that. We see this one here that says stop. It's a method. You have to put parens after it, and it says this stops playback and resets to the start of the sample. That's what we want. So I'm going to head back to CircuitPython, and instead of passing while audio.playing, I want to check to see if a touchpad is being pressed. So I'm going to copy this little component here. Now I'm going to make a change to the play sound function so that I can pass in a touchpad number so I can check to see if that touchpad is being pressed, and if the audio is playing, if that pad stops being pressed, then I'm going to call audio.stop. So first, to be able to pass in the number of the pad that was pressed, I'm going to add a parameter in my function call up here. After file name, I'm going to say comma, and I'll call this pad_number. Then while audio.playing, I'm going to paste in touchpad I.value, but I'm going to put an if in front of that. Now this line is the same as the line below, but I don't want to check to see if the pad is being touched. I want to see if the pad is not being touched. So first I'm going to replace the I in touchpad bracket I with pad_number, the value that I'm passing into this function. And to check when it's not true that this pad is being touched, I'll just put the word not out front. That's the same, by the way, as touchpad number.value == false. I like the way that the not reads here, so I'm going to keep that in instead of saying == false. You can use whichever statement you think is better. But if the pad is no longer being touched, I can delete the pass down here. I don't want to just wait. Instead, indented below this if statement, I'm going to call audio.stop, open and close parens. Remember, this is a method, so I need the open and close parens. But don't forget, very important, we changed the play sound function. We're now passing in a value for the pad number. So down here where I call play sound, I need to say comma I in this call. But this should work. Let's open our serial console, select save. I see no errors. Let's try this out. So that module seems to be working, and when we take our finger off the pads, look at that, we're stopping, we're starting again at the beginning. When we press the pad again, mission accomplished.
Watch this, yo. Watch this, yo. Watch this. Watch this. Watch this. Watch. Yo.
So nice work, Funky Coder. Why don't you head over to your CircuitPython school folder and make sure that you save this so you've got a backup of all this excellent code you just wrote. I'm going to name this Wave Stop Mount SD. Close the tab. Reopen code.py for my CircuitPy volume, but in this big learning-packed lesson, we learned how to work with an SD card, we learned about SPI versus I2C, and we wired the SD card to our Pico. We formatted the SD card, copied files to that card, and mounted the card for use with our code. We played MP3s off that SD card. We played WAV files off that SD card. We wrote our first module so that we can reuse our code that we created to work with an SD card, and we learned to stop the playing of a sound. Now rock out, Coder, as part of your celebration of the big learning, but be sure to come back because there's much more in store.